Hello, and in today's video, we're going to be reviewing Chapter 19, Ketone and Aldehyde Nucleophiles. The basic trend is that basicity and nucleophility increase down the row, and nucleophility increases down the column, and as basicity decreases up the column. Here are the nucleophiles we learned. They're grouped into carbon, nitrogen, and oxygen, with carbon being the strongest and nitrogen being the medium. In the carbon group, we have cyanohydrin, Yllid, and the Wittig reaction. And then we have Grignard and organolithium nucleophiles. In the nitrogen, we have primary amines and secondary amines. Primary amines yield L-amine, and secondary amines yield N-amines. Oxygens have hydrates, alcohols, diols, and the Jones reagent, and they all contribute to the formation of hemiacetals and acetals. So first we have carbon nucleophiles, and we're going to do cyanohydrin. Let's take basic examples. Here is an oxygen ketone, and we're going to treat it with this cyanohydrin. The lone pairs will attack this carbon center, kicking off electrons to the oxygen, making it negatively charged. Now the lone pairs will attack this hydrogen, causing it to form an alcohol. This is the final product, plus Cl minus. So that was a cyanohydrin reaction. For a Yllid, we can take this ketone, for example, this most basic ketone. These lone pairs will attack there, causing that to occur. Now, negatively charged oxygen with the CH2 group. Now these lone pairs will attack, or will create a bond here, causing the formation of a oxophosphatine. A ring rearrangement will occur, yielding this final product. CH2 and the oxygen will be bound to this group. It's important to notice how the group attached to the PPH3 and the oxygen of the ketone will actually just switch places. Okay. Lastly is the Grignard and organolithium. So here we will take this Grignard reagent and react it with this aldehyde. And the ether solvent and hydronium ions. That's the Grignard. Now we'll go over organolithium. Here we can use a similar structure. Lithium, it's very similar to the Grignard reagent, that's why they're grouped together. And here we can have just a ketone. CH3, CH3. Forgot to draw the arrows, but they're all very similar. And this is done in a hydronium ion also. And then the lone pairs, the oxygen, depronate, resulting in the formation of OH. Right, that is the final product. So for carbon nucleophiles, we had cyanohydrin, Yllid, Grignard, and organolithium. Now we'll move on to nitrogen. And we had primary amine, which results in the formation of an almine, and we had secondary amine, For this example, we'll use this aldehyde plus this secondary amine yielding the final enamine product. This is a secondary amine. Next, we will go. It is important also to mention that these two reactions occur the most in biochemistry because nitrogen is very commonly used in the human body because it's in the medium between carbon and oxygen in terms of being a medium reactive nucleophile and base. So for primary amines, this will be our reaction. We'll start with this basic ketone and react it with this primary amine. I'm just going to move this down. There. The first step will be a proton transfer, just in the reactant, which will give lone pairs to the nitrogen and result in this alcohol. Of course, this will add a hydronium ion, so now H3O plus. Okay, this will deprotonate here, resulting in water. These lone pairs will move there, and these will move there, resulting in the elimination of water. Now, carbon will be bound to nitrogen, and our double dagger and hydrogen. These will have the two R groups. Now, the alamine will form. This will be the final product, alamine, when, I forgot one step, water will deprotonate this hydrogen ion and move the lone pairs back to the nitrogen, which stabilizes the charge. Here we have nitrogen, R double dagger, and then the R dagger and R. That will be, this is a carbon, not an oxygen. This will be the alamine. And that is the nitrogen reactants, or the nitrogen nucleophiles. Next we'll move to oxygen. Oxygen. And our first reaction will be hydrates. Hydrates. I'm just looking for a good example to show. So let's take this basic ketone again and react it with H plus, and a hydrate will form, OH. So that would be classified as an acetal. And the mechanism proceeds as follows. H3O plus, these lone pairs push, and this results in OH plus. Now we take H2O, which causes this to happen. And then the lone pairs again from H2O deprotonate. And the final product is this one. Okay, so that was the formation of a hydrate. Now we should go over I forgot to mention that in the formations of these, an acetal would be that. This is an acetal, the most basic way you could write an acetal. And this would be a hemiacetal or hemiketal. let's take this cyclohexane bound to an oxygen. Cyclohexanone plus 2CH3OH reacting with toluene sulfonic acid will yield this we can use this example again, and we can ROH and H plus will be the reactants. This will yield this hemiacetal. If we react it again using another equivalence of this, an acetal will be formed. So that's a hemiacetal, this is an acetal. These are the formations. Now we react this with H plus H2O. This will hydrate. So those are basically, this will yield hydrate. Those are the three, and this is the basic mechanism for all that occurs. It's just a mix of deprotonation and transfer of pairs, lone pairs, that yield the products.